Welcome to Lab 4, Circuits. The purpose of this lab was to investigate the current flowing in a circuit and the effect of resistors and capacitors on a circuit. We also examined how the capacitor charges and discharges and observed how the current and charge buildup in the capacitor change over time. The model in this lab was the PhET Online Circuit Kit lab. Some fundamental physical principles present in this lab are circuits, the node rule, the loop rule, electrical resistance/resistors, and capacitance/capacitors. The main result of this lab was that the current was 0.02 amperes in the first circuit. The current took the path of least resistance. The ammeter and voltmeter did not affect the current flow when connected correctly. The time constant RC is equal to 6 seconds, and the greater the resistance, the longer it took for the capacitor to charge. In this lab, we made some circuits, and in a circuit, the electric field is parallel to the wire and flows from the positive to negative terminal of the battery. The node rule states that the current flowing into a junction has to equal the current flowing out of the other junction. The loop rule states that the voltage change across the circuit in a round trip has to equal 0. Both of these rules are as a result of the conservation of charge. We also studied resistance, which can be given by Ohm's law, which states that the change in voltage is equal to the current times the resistance we're driving the current past. We also studied capacitance, and in this equation we see that the capacitance is equal to the charge buildup in the capacitor divided by the absolute value of the voltage drop across it. We also had to look at the voltage with respect to time in RC circuit in order to make a graph and find the RC value for this circuit. In the experiment, the system is a circuit and the surroundings is the Earth and the universe. The initial conditions was that the circuit was composed of two 1.5 volt batteries, a 45 ohm resistor, and an 100 ohm resistor all in series. Using Ohm's law, the current was determined to be 0.02 amperes. The ammeter measured the same amperage. We connected two emitters on opposite sides of the circuit. One emitter was placed before the resistors and the other after. We then replaced one of the emitters with the voltmeter connected in series and observed the reading on both meters. We then measured the voltage across various points of the circuit, shown in the image on the right. We added the voltage drops around the circuit and compared it to the EMF of the battery. We then drew a graph of potential between the different points, and we used voltage drops to calculate resistance of both resistors, the wire, and the ammeter. Then we connected a 9 volt battery to a 10 ohm bulb and a 200 millifarad capacitor in series. After the capacitor charged, we connected it to the bulb. We then observed what happened to the current in each. With a stopwatch, we measured the time it takes to charge and discharge the capacitor using a 10 ohm bulb, and it did the same thing with a 20 ohm bulb. We then made a circuit with a 9 volt battery, a 30 ohm light bulb, and a 200 millifarad capacitor. We measured the initial voltage drop across the capacitor, and after it was charged, we connected the capacitor to a light bulb and got voltage versus time measurements using a stopwatch and a voltmeter for 20 seconds. We then plotted the Ln voltage drop divided by the initial voltage drop versus time plot. The slope of this graph is supposed to be -1 over the time constant RC. We then compared it to the computed value. The results include that the ammeters measured 0.02 amperes across the whole circuit. When we disconnected the circuit and added the voltmeter, the measured current was 0 amperes. In order for the voltmeter not to alter the current, it has to have an incredibly high resistance so no current flows into it. When connected in series, the voltmeter has such a high resistance that virtually no current flows through it, so the current measured 0 amperes. This is a list of the various voltage changes across the circuit and the addition of the various voltage drops across the circuit in a round trip. And as we can see, it's 0 volts. And the image on the right is a graph of all this. And as you can see, the final voltage is 0. The principle of a voltmeter is that it has an extremely high resistance, and since electrons like to take the path of least resistance, it flows through the normal circuit instead of the voltmeter. Therefore, the current isn't affected, and the ammeter reading does not change. Again, electrons like to take the path of least resistance, so the electron flow through the ammeter instead of the resistor. The current is as if the 100 ohm resistor wasn't there. The results also include that when the capacitor is connected in series to a bulb and battery, the light bulb lights up, dims, and then turns off, and charge is accumulating in the capacitor. When the capacitor was charging and discharging, the current was decreasing in both cases. It takes about 8.65 seconds to charge and 7.96 seconds to discharge the capacitor with a 10 ohm light bulb, and 11.9 seconds to charge and 14.81 seconds to discharge with a 20 ohm light bulb. The initial voltage drop across the capacitor is measured to be 9 volts, and this is a graph of the natural log of the voltage drop divided by the initial voltage drop versus time. The slope of the graph is -0.1666 repeating, so the RC is about 6 seconds. The resistance of the light bulb is 30 ohms, and the capacitance of the capacitor is 0.2 farads. So if you multiply these values together, you get 6 seconds. So the expected and calculated RC values agree. The model was the experiment, and it was conducted under ideal circumstances because it was online. Therefore, there are no sources of error. A circuit in real life would not be ideal. An ammeter would have resistance, the cable would have resistance, etc. Therefore, the current measured would be less, and it would take longer for electrons to move through the circuit. An ideal simulated ammeter has a resistance of 0, so as to not affect the circuit. A real ammeter would have low resistance, but it wouldn't be 0. Therefore, it would affect the current by a tiny amount. The current measured would be less than the current in the online lab. According to the lab, the voltage drop across the capacitor is equal to the initial voltage change times e to the negative t over RC. In the online lab, the resistance in the circuit would be 0, but the time required to charge the capacitor would be 0. In other words, the capacitor would charge instantaneously. However, an ideal wire has a resistance of 0, but in real life, the wire does have resistance. Therefore, the capacitor would charge faster, but not instantaneously.